Question 6, Part 1, Pump Storage Power Station. It says a diagram, not to scale, shows a pump storage power station used for the generation of electrical energy. Basically what happens with this is that water is pumped up into a reservoir, into a tank, and then it is allowed to drop down again through a turbine and create electrical energy from that falling water. So it's often used when you have off power times, when there is extra power available. That is when the water is pumped up, and then when it's peak times, when you need maximum electrical energy output, it is allowed to fall through the turbine. So it's almost like a battery system. So water stored in a tank is allowed to fall through a pipe to a lake via a turbine. The turbine is connected to an electrical generator. The pump storage AC generator system is reversible so that the water can be pumped from the lake to the tank. The tank is 50 meters deep and has a uniform area of 5 times 10 to the 4 meters squared. The height from the bottom of the tank to the turbine is 310 meters. The density of the water is 1 times 10 to the 3 kilograms per meter cubed. First question, show that the maximum energy that can be delivered to the turbine by the falling water is about 8 times 10 to the 12 joules. So we're looking at all this water in the tank. Notice it says it can be delivered to the turbine by the falling water. So we're looking from that water in the tank falling down the 310 meters. We want to see the total energy. Well, basically what we need is using our formula EP is equal to mgh. We have got our height, that is 310. We have 9.8 or 10 meters second to the negative 2 is our g, but we need to get a value for our mass. Now remember that the density is equal to your mass over your volume, so mass is equal to your density times the volume, and we have our density is 1 times 10 to the 3, so it's 10 to the 3 kilogram per meter cubed. And now we've got to find our volume, and our volume needs to be in meters cubed because our density is meters cubed, and we're told that our cross-sec has a uniform area of 5 times 10 to the 4, so it's 5 times 10 to the 4 times by the height, which is 310, and that gives us 2.5 times 10 to the 9 times 10 to the 9, and that there will be your mass. That will be kilograms, and we're going to put that into this formula over here. So our total energy, EP, is going to equal 2.5 times 10 to the 9 times 9.81 times 310. And you can work that out. So that's going to be 2.5 exponent 9 times 9.81 times by 310, and that gives a total value of about 7.6 times 10 to the 12, and that will be joules, and that's what you want to work out. 7.6 rounds down to 8 times 10 to the 12 joules. Now it says next that the flow rate of the water in the pipes is 400 meters cubed per second. Calculate the power delivered by the falling water. So in looking at this, we've got here it's 400 meters cubed per second that is going through, and we want to calculate the power delivered for the falling water. Well, there's different ways of doing this. What I would think that you need to do, this is that you know that the rate is 400 meter cubed per second. So I'm going to look at an energy per meter cubed, find an energy per meter cubed, and then multiply it by the 400 meters cubed per second. that will give you a power value. So if you take this 8 times 10 to the 12 joules, that's the total energy that you have available for all that volume, and you divide it by 5 times 10 to the 4 times by 50. This is the total volume. So then we're going to get from this, we're going to get a joule per meter cubed, like that. So that will be a joule value per meter cubed. So let's just do that. So I get 8 exponent 12 divided by 5 exponent 4, and I need to put that in brackets there, so let me just put an insert. And I'm going to times that by 50, and we get here, we get a value for this of 320,000,000, and that's joules per meter cubed. So that's for every meter cubed you're developing that many joules, and we're told that we get 400 meters cubed per second. So if I multiply this by 400 meters cubed per second, you see that my meters cubed getting out. I'm going to get my final value will be a joules per second, which is a power that's a watt. So I multiply that by 400 times 400, and I get let me just work this out. 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 1.28 times 10 to the 9 watts will be my power output, and I'll write that about 1.3 times 10 to the 9 watts will be my final value that we get out there. Now, so you could also have worked this out in a different way. You could have also worked out how long it would take, the total time it would take for all this water to run out. And once you know the total time, then you could divide the total energy divided by that total time, and that would also give you a power per second. So there's two different ways of doing that. Maybe a third way, maybe you can think of a different way. Now going into this question over here, question B, we have here that the energy losses in the power station are shown in the following table. So we get sources of energy loss: friction and turbulence of water in the pipes, friction in turbine and AC generation, and electrical heating losses. So we got that. Calculate the overall efficiency of the conversion of gravitational potential energy of water into electrical energy. Well, the overall efficiency would be the output over the input. Now these are our energy losses, so if we just add these together, I'm going to get 47% is lost. Therefore, obviously we're going to have 53% is going to be my total efficiency. That will be the output over the input. Then it says sketch a Sankey diagram to represent the energy conversion of the power station. Now we know that a Sankey diagram, that we start off with our input power. So I get to my input here, and that length corresponds to 100%. And so the amounts that are coming off need to be proportional. So I get friction and turbulence in the water. So I'm going to get a situation here where you're going to get some is going to come off in the form of turbulence, and also some is going to come off in the form of friction. Now that's a total of 27%. So really this value should be just over a quarter of the total amount. So let's say it's going to be like that. and that should correspond to that. Then we get our friction in the turbine and in the AC, that's 15%, so that goes along like that. And we get this coming off here, so it's a further 15% coming off there, something like that. And we get 5% is coming off over here as finally that, and that will be a very small value. And so this would be my total end output there. Now this should correspond to 53%, so it should be slightly more than half. Now as you can see, my diagram isn't great. You should put in here your friction, your heating losses, that's right, so we get that. So we get our turbines water, heating losses, and this was also over here be heating losses over here. Okay, so something like that. And then finally we've got here these two questions. The electrical power produced at the AC power station is transmitted by cables to the consumer. Outline how the energy losses in the transmission are minimized. Well, basically what happens is you step up the voltage and step down the current. So you make it high voltage, low current. So you have what we call a step up transformer. Now because power is equal to I squared R, your losses, your power losses are an I squared term. So you want to try and minimize that as much as possible. And also what you can do obviously is you can have thicker cables, and the materials that you use to have a lower resistivity, to have a lower, remember, resistivity. And then it says state one advantage and one disadvantage that a pumped storage system has compared to a tidal water storage system. Now it's very important to note here that they are comparing these two things, so you have to frame your answers as you relate these two things together. So you've got you're looking at your pump storage system as to your tidal water storage system. So in looking at this, with a pump storage, the main advantage with this is that we can control the power output. So you are in control. You can let that water out when you want it. So you can control that power output. When you need the extra power, you can get it. The disadvantage with it is that it's not constant. With the pump storage system in difference to the tidal water, you have to pump up the water. So you are always putting energy in. You have to put energy in, and then you get it out afterwards. So where with tidal, it's always there. Your energy is coming from the sea, so it is available all the time. But with sometimes your tidal power may not be as much as others. You get your high tides and your low tides and your neap tides and so forth, so it's not always as available, but you don't actually have to put in any energy for the tidal power.